Dielectric investigations on Pentyl P-Hydroxy Benzoate. Abstract cavity perturbation technique and plunger method in microwave frequency region to obtain dielectric constant and further to compare the data on both techniques, for static dielectric constant by LCR bridge and for measurement of high-frequency dielectric constant through Abbes refractometer were used in order to calculate relaxations times. Higasi method was used for dipole moments in the dielectric study for different concentrations of the binary system of nonyl P-hydroxy benzoate, 9Hb, and isopropanol and benzene as solvent. There is an increase in the relaxation time as the concentration of the benzoate is increased in solute system in different concentrations of nonpolar solvent benzene, and there is a decrease in the dipole moment as the concentration of the benzoate is increased in solute system in nonpolar solvent benzene, and they are attributed to the formation of hydrogen bond between the solute systems. Keywords: cavity perturbation technique, plunger technique. Dielectric constant, relaxation time, dipole moment. 1. Introduction. Pentyl P-hydroxy benzoate has been used in various fields, viz. food preservatives, cosmetic preservatives 1 to 3, whereas alcohols have found various applications for including commercial use in medical and other fields, for example very effective against a broad spectrum of microorganisms including bacteria, fungi, and viruses such as HIV, hepatitis B, and respirator syncytial viruses. Most of the dielectric relaxation processes reported in the literature were studied for dilute solutions of polar substance in nonpolar liquids. The nonpolar liquid does not itself undergo relaxation but alters the relaxation time of the solute molecule by reducing the internal field and changing the viscosity. The dielectric constants and losses of binary mixtures of polar components as function of temperature found 2 maxima for mixtures of an associated and a non-associated liquid, but only 1 maximum for mixtures containing only associated liquids or non-associated liquids as investigated by Spolamach 511. On the basis of this observation, he suggested that dielectric relaxation involves the disturbance of a relatively large region in the liquid, and that a mixture of associated and non-associated liquids is not microscopically homogeneous. However, measurements at several microwave frequencies and at different temperatures have been reported in literature 3,5-9. The dielectric absorption of some benzene derivatives and their binary mixtures has been studied by Boru et al. 10 at 3 cm. Investigation of dielectric relaxation in tributyl phosphate were carried out from susceptibility and conductivity measurement under microwave field by Bachar et al. 11 in the range of temperature from 25 degrees C to 45 degrees C. The relaxation time, dipole moment, and the thermodynamic parameters for the dielectric relaxation as well as for viscous process were measured. They discussed the results on the basis of molecular size, molecular polarity, molecular environment, molecular interaction, effect of localization of charge density, and contribution arising from the formation of hydrogen bond structure. Dielectric studies were carried out on some hydrogen-bonded polar binary mixtures of alkyl P-hydroxy benzoates and isopropanol by Sreehari Sastry et al. 12. A resonant cavity method intermediate between the Hartshorn-Ward method and the microwave resonance method suited for measurement on low-loss materials in the frequency range has been described by Works et al. 13. They measured the dielectric properties of a variety of low-loss materials at 200 MHz. Birnbaum et al. 14 observed that the microwave resonance method is used to determine the dielectric constant and loss of liquids, solids, and very lossy gases provided the cavity volume is only partly filled with absorbing dielectric. A microwave resonance technique suited for measurement on low-loss liquids has been described by Pitt and Smith 15. Cavity perturbation method is widely used in the characterization of dielectric 16, magnetic 17, 18, and superconducting materials 19. The different microwave cavity perturbation techniques are discussed by Raman 20. The application of microwave cavity perturbation technique for the study of transients in semiconductors is becoming popular due to its simplicity in measurement procedure and high sensitivity. Effects of quality factor, sample size, and coupling factor of the sensitivity of the measurement are discussed. 21. The complex dielectric constant for different liquids are measured using waveguide transmission line techniques at 4 frequency ranges. The results are discussed and compared with the literature and the calculated data using Debye's method. 22. A comparison is achieved between the 4 positions of the cavity from which the optimum cavity position is selected, along with the limitations of this method are represented in 23. In continuation of our dielectric work in binary systems, cavity perturbation technique and plunger method in microwave frequency region to obtain dielectric constant and further to compare the data on both techniques. Further, for static dielectric constant by LCR bridge and for measurement of high-frequency dielectric constant through Abbes refractometer were carried out in order to calculate relaxations times. Higasi method was used for dipole moments in the dielectric study for different concentrations of the binary system of Pentyl P-Hydroxy Benzoate, 5-HB, and Isopropanol and benzene as solvent. 2. Materials and experiments. A. Materials. Pentyl P-Hydroxy Benzoate, 5-HB, of extra pure quality with 99.5% purity was supplied by M/S Frinton Laboratories Inc., USA. Both isopropanol and benzene were supplied by Qualigens. Both of them were XLR grade and were double distilled before use. Benzene is used as solvent. The binary system of Pentyl P-Hydroxy Benzoate, 5-HB, and isopropanol is used as solute in the preparation of solution. The structure of 5-HB is shown in Fig. 1. B. Measurements. 5-HB is dissolved in isopropanol in various concentrations. The various weights of 5-HB for each concentration is given for 26.5 ml of isopropanol. The mole fraction of 5-HB in isopropanol from 0.02, 0.03, 0.04, and 0.05%, the weight of 5-HB of 1.62949, 2.46943, 3.32688, and 4.20237 grams respectively. All the weights are measured using a single pan electronic balanced Hona make, Model 100DS with an accuracy of 0.01 mg. Each concentration of solute is diluted with benzene in volume fractions of 90% benzene and 10% solute, 80% benzene and 20% solute, 70% benzene and 30% solute, and 60% benzene and 40% solute. The dielectric studies are carried out using LCR bridge, static dielectric constant, the microwave bench adopting plunger technique and cavity perturbation technique 4-7,24 method, in X-band. The resonant frequencies, and correspond to empty cavity, cavity with empty holder alone, and lastly cavity containing holder with the sample. The dielectric constant is obtained through the equation 0F. 3. Results and discussion. In this section, the experimental results obtained from the optical, static, and microwave frequencies for different concentrations of 5-HB in isopropyl alcohol, and it is diluted in a nonpolar solvent medium benzene. Since the solute, 5-HB and isopropanol, is a highly polar compound, highly saturated wave pattern is obtained in the measurement of complex dielectric constant at microwave frequency by using the plunger method. Due to the high loss nature of the sample, it is not possible to measure the dielectric constant of high concentrations of the 5-HB in isopropyl alcohol systems. In order to study the properties of these systems, we diluted the above system for different concentrations of nonpolar solvent medium benzene. Diluting the system in nonpolar solvent medium, it is useful for studying the interaction between the 5-HB and isopropanol. From the standing wave pattern in the microwave frequency region, dilution studies of different concentrations of solute, 5-HB and isopropanol, in nonpolar solvent medium is easy to obtain the dielectric constant and dielectric loss. The measurements are done at room temperature, 300 OK. Dielectric constant. The different concentrations of solute system, 5-HB and isopropanol, are dissolved in nonpolar solvent benzene at various volume concentrations. The dielectric constant of each concentration is measured at optical frequency, low frequency 1 kHz and microwave frequency 8.83 GHz at room temperature. The complex dielectric constant, Asterisk equals J, in the X band, 8 to 12 GHz, microwave frequency region is measured by using the cavity perturbation and waveguide plunger techniques. In cavity perturbation technique, the signal obtained for without and with sample is fed to CRO from the tuned detector, which is shown in plates 3.1 and 3.2 respectively. The measurement of dielectric constant and dielectric is made. Standardization of the cavity technique. The data was obtained from cavity perturbation technique with the samples ethyl P-hydroxyl benzoate, EHB, proyl P-hydroxyl benzoate, PHB, and butyl P-hydroxyl benzoate, BHB, at room temperature for different concentrations. It is observed that the values are in good agreement within the accuracy of the techniques involved. On the compound 5HB, the experiment is repeated using cavity perturbation and plunger techniques for different concentrations at room temperature, and the data is shown in Table 1. Table 1. Dielectric data for various concentrations of 5HB and isopropanol in benzene using cavity and plunger techniques. From the above data, the obtained values from both cavity perturbation and plunger techniques of dielectric constant and dielectric loss are same within the experimental accuracy at microwave frequency. Hence the data from any technique can be used to calculate the relaxation times. The data on dielectric constant, relaxation time and dipole moment is given in Table 3. Table 3 comprehensive data on dielectric constant, relaxation time, dipole movement for various concentrations of 5HB and isopropanol in benzene. A representative readings due to plunger method is given in Table 4. Table 4 microwave bench readings obtained by moving plunger in 0.02% of Pentyl P-Hydroxy Benzoate, 5HB, in isopropanol taken as solute and benzene as solvent for concentration of 90% benzene and 10% solute. Coal plots and relaxation time. All these data were used to fit in an Argand diagram. Versus. To calculate the relaxation times. It is observed that a distribution of relaxation times as witnessed from coal arc plot instead of Debye arc plot, which signifies the distribution of relaxation times. Eventually a macroscopic relaxation time, predominant relaxation time, is computed using coal plots. The corresponding parameters obtained from coal arcs such as distribution parameter and the corresponding angle equals, where M2 is molecular weight of solute, D1 is density of solvent, 0.1 is the dielectric constant of solvent, benzene, A0 and A, are respectively the slopes of O and. With respect to the concentration, the other constants have the usual meaning. The data required for calculating dipole moment are given along with the dipole moment at each concentration in Table 3. The values of A0 and A are found from the graphs of O, static dielectric constant, and Vs concentration respectively, which are shown in Figs 4 and 5. It is evident from the data given in Table 2, the dielectric constant increases with the increased frequency. The microwave data show that these compounds are polar in nature and correspondingly the dielectric constant is a complex quantity. The relaxation time is found to increase in magnitude for a given concentration of 5HB in isopropanol with the increase of dilution in benzene, which shows that the molecules are free to rotate as benzene concentration increases. From the Table 2 it can be said that, the static dielectric constant, S static, increases with the increase of concentration of solute. Comparing the static dielectric constant of EHB 25, PHB 26 and BHB 27, it can be concluded that when concentration of solute increases, static dielectric constant also increases. In the microwave region also the dielectric constant increases with the increase of concentration of 5HB in binary system. But at optical frequency region the dielectric constant decreases when the concentration of solute increases in the binary system. It is due to dipolar polarization contribution decreases at high frequency. At high frequency the dipolar polarization disappears and only atomic polarization or electronic polarization is present. The dielectric constant decreases with the increase of frequency, from static, low frequency, to optical, high, frequency. It means frequency increases, the dipolar polarization contribution decreases and vanishes. At static frequency all polarizations are present. The relaxation time increases with the increase of concentration of solute. This behavior may be attributed to the formation of hydrogen bond between isopropyl alcohol and 5-HB. The phenomenon of dielectric relaxation of the binary mixture of polar molecules in nonpolar solvents at microwave frequencies has been attempted by many research workers. Raman Kumar and V.S. Rangrad 28 also calculated the binary mixture of N-methylacetamide, NMA, and acetonitrile in benzene. They concluded that some molecular interactions exist in the binary mixture. The same may be attributed to the present case, that is, forming of hydrogen bond between 5-HB and isopropanol. The strength of hydrogen bond reflects in the corresponding relaxation time and dipole moment value. 4 conclusions. The low-frequency static dielectric constant and microwave frequency electric constant increased with increase in the concentration of the solute binary system, benzoate and alcohol, in nonpolar solvent benzene at room temperature. The optical refractive index value decreased with increase in the concentration of the solute binary system, benzoate and alcohols, in nonpolar solvent benzene at room temperature. Dipole moment and relaxation times are calculated. There is an increase in the relaxation time as the concentration of the benzoate is increased in solute system. In different concentrations of nonpolar solvent benzene, and it is due to the formation of hydrogen bond between the solute systems. There is a decrease in the dipole moment as the concentration of the benzoate is increased in solute system in nonpolar solvent benzene, and it is due to the formation of hydrogen bond between the solute systems. The data obtained through the plunger and cavity perturbation techniques is similar, but the advantage is less quantity of sample is required in the cavity technique. V. Acknowledgements. One of the author, SSS, is grateful to UGC New Delhi for providing BSR Faculty Fellowship No. F4-5, 11/2019, BSR, DT 17-8-2020. The authors are also grateful to UGC Major Research Project No. F34-12/2008, SR, dated December 30, 2008. The authors are grateful Professor V. R. K. Murthy, IITM, in conducting the experiments.